In this module, we will look at a case study of a disk allocation algorithm as implemented in the Unix file system. We are looking at the details of inode blocks, directory structures, and how to link files using hard link and symbolic or soft links. The Unix file system implements a slightly different variation of indexed allocation. Just a reminder, with the basic index allocation, the directory entry contains a pointer to an index block, and the index block has multiple pointers to the data blocks of the file. In the theoretical description, an index block is just a data block that is used for holding pointers to the actual data blocks instead of holding the actual data of the file. In the Unix file system, index blocks are called inode, and they are managed differently from data blocks. In addition to holding pointers to the file data block, a Unix inode also holds the metadata like owner, permission, shown in green boxes here. Besides the metadata, the inode also holds up to 15 pointers to the data block. The first 12 pointers are called direct pointers because they point directly to the data blocks holding the data of your file. The next 3 pointers are called indirect blocks because they are pointing to a data block that holds pointers to more data blocks for your file. Why do we need the indirect blocks? In case a file requires more than 12 blocks, then one of the indirect pointers will be used to hold more data blocks. And to allow handling huge files, the Unix file system is using a multi-level indexing scheme, and the depth of the index can go as high as 3 levels deep. Now, if you compare the theoretical index block as we learned in index allocation with the Unix inode, the direct pointers are basically similar to the index block where they both hold pointers to your data block. It is important to understand that in Unix file system, one inode is allocated per file or directory. Let's look at an example here. So let's say we have a structure of multi-level directories starting from the root node. Just to remind you again, in Unix, everything comes from the root directory. In the next few pages, we will discuss the internal structure of Unix directories. But let's first inspect the relationship between a directory and its parent. Just a reminder, when you run ls with -a option, you will see 2 extra output from your ls output, the dot, which is referring to the current directory, and the double dot, which refers to the parent directory. So we will start from the root directory. In Linux file system, the root node is associated with inode number 2. When you see the output of ls-a, when you run it on the root directory, you will see the inode number. So the leftmost number on all this output here tells you the inode number. Because we are running ls from the root directory, that's why you see the self, which is the current directory, has the inode of 2. But because the parent of root is the root itself, that's why you will see that on the second line, the double dot directory entry is actually the same inode number 2. Now in our structure, let's assume that home is a subdirectory under the root directory. And if you look at the output of the third line from here, we know that the inode of home is 256. Now, if we run ls-a on our home subdirectory, then basically in my example, you will see one entry, dulimrh, which is a subdirectory of home, but because you are running ls with the -a flag, then you will see the 2 extra lines dot, which is referring to self, and then the dot dot referring to the parent. And from the structure, we know that the parent of home is the root directory, and that's why you see the inode of dot dot here is inode number 2, because number 2 is the inode of the root directory. From the output of the first block, we know that the inode of home is 256, and you see the same number 256 again when you run ls on /home, because this dot refers to the current directory, which is /home. And if you continue running ls on different subdirectories, so in next block of output, I'm running ls -l-a on this subdirectory, and the inode of this subdirectory is 9000715. And again, when you look at the output from this ls -a command, the dot entry is associated with inode 9000715, and then the double dot, which is the parent, should be the inode of home, and 256 is the same number that you see in here, which is also the same number that you see in here. So continue downward, and if we run again ls -la on the public subdirectory, and you can see from here the inode of public is 9001015. That's why you see the entry of the dot output is 9001015, but the double dot, which is the parent of public, is home Dolimar, and you know that the inode of home Dolimar H is this number 9000715. So that's why you see on the double dot entry, it will show you the inode of the parent. So this diagram shows how different parts of an inode is used. The green boxes here holds the metadata of your file, like the permission mode, the owners, the timestamp, the file size, and the link count. And the yellow boxes here are pointers to your data block. And again, I want to emphasize that in Unix, inode blocks are different from data blocks. The screenshot of the Unix terminal shows you the output of ls and stat. If you look at the output of stat, the file name is fetched from the directory entry, but the rest of the output is fetched from the metadata inside the inode block of that file, because there is a link between the directory entry to the inode of that file. In our case, inode number 241 is the inode of 1.txt. So the rest of the output, like the access time, modified time, change time, are fetched from the metadata, and the group owner, the user owner, like group owner, that number, and the user owner, that number, is fetched from the metadata. So the yellow boxes hold pointers to your data block, and the pointer can be either a 4-byte pointer or an 8-byte pointer. So in Linux ext file system, you can you can prepare the file system either to use 4-byte pointers or 8-byte pointers. So using 4-byte pointers, the size of an inode can be between 90 bytes to 100 bytes or more. How do we get 90 bytes? Well, if you count the number of pointers, we have 15 pointers, 12 from here and then 3 from here. So total of 15 pointers. If each pointer is a 4-byte address, then total for the pointers would be 60 bytes, and the total for the timestamp will be between 32 bytes to 48 bytes, depending how many bytes you use for size and timestamp, because timestamp can be either a 4-byte data or an 8-byte data if you want to get a more precise time resolution. Now, if you use an 8-byte pointer for your data blocks, then the size of one inode can be between 150 bytes to 180 bytes. I want to emphasize that in Unix, inode blocks are different from data blocks. And a data blocks can vary in size between 512 bytes to several kilobytes depending on how you prepare the file system. So the yellow boxes are pointers that point to data blocks of your file. And there are two kinds of pointers. The first group is what we call the direct pointer. With a direct pointer, each pointer directly points to your data of the file. But with indirect pointers, and we have 3 of them, each pointer is pointing to a block that holds more pointers to point to more data blocks. So that's why we call them indirect pointers. Let's use this hypothetical example to understand better the relationship between inode, directory entries, file name, and other metadata information. So I'll be using this as an example. Let's say under the projects directory, we have 2 subdirectories and 4 files, 1, 2, 3, 4. And total under the subdirectory projects, we have 6 inodes associated with these items. So 2 inodes for the subdirectories and then 4 inodes for the file 1, 2, 3, 4. So let's assume that the project subdirectory is directly under your home and you run ls-li on your home, and we have this output. So we know that the inode of the project's directory is 9322. If you focus only on the entries inside the project subdirectory, technically you should see 4 items. The first item is CS452OS, the second item is homework 4, the third item is CS263, and then the fourth item is the PDF file. And that's why you see 4 items in the directory entries of project. Remember, at this point, the 2 files, the C file and the TXT file under the CS452OS is not listed in the project's directory. These 2 files are under another subdirectory. And if you try to match the output of ls-li down here with the diagram of directory entry, then you should see the correspondence between the numbers. So the subdirectory CS452OS has an inode of 4781, and that's why you see the same number down here and up here. And the file homework4.txt has an inode number 6234, the same number that you see inside this box. Now, using this example, you should be able to fill in the missing number from here. So what do you think the missing number inside that box? Well, you can use the output from ls-li down here to fill in the missing entry in the green box. So the output down here tells you that the inode of CS263 is 7144. So that means that number should be 7144. So how about the double dot? Well, the double dot here refers to the parent of the project's directory. And in our example, the parents of project's directory is your home directory, but we don't have any information about the home directory. Anyway, but we can fill in the dot entry because dot refers to yourself. From the output of ls down here, we know that the inode for projects is 9322. So that means that number is also 9322. Now, let's say you go deeper into the subdirectory CS452OS, and if you look at the 2 files under CS452OS, and you should be able to fill in the 2 missing numbers in here. So, what is the dot? The dot is self. That means this number should be the inode of that directory. And you can use this information up here, 5781, or you can also use the information from the output of ls-li. The dot directory entry has the inode number 5781. How about the double dot? The double dot is the parent. In our case, the parent of CS452OS is the project's directory. And if you look at the output from ls-li from the gray box, the inode of projects is 9322. So that number here is supposed to be 9322. So a directory entry in a Unix file system is just a pair of file name or directory name and inode number. We will look at more details about the link count in the next few slides. Let's look at the details of inode 6234. 6234 is the inode of our homework4.txt file. And if you look at the output from the gray box, we can see more details. The metadata of that file, the permission mode is read-write only by the user. And you see the permission mode here. The user owner is user1. The name of user1 is in the metadata. And the group owner is student. And the date, we just show you one of the dates, one of the timestamps. This is October 2nd, 2013. And the file size, 7,000 something. And the link count is 1. And then another inode is also shown here, inode 5781. And if you look at the directory entry, 5781 is the inode of our subdirectory CS452OS. And if you look at the detail of that output, and you will see the permission mode, the same permission mode that is recorded in the inode, the user owner, the group owner, the file size, and the last modification date, which is January 17, 2013. And the link count is number 2. The Unix file system gives you a feature that will let you create links of files from one directory to another. But why do you want to use this feature? Let's say you and your classmate are both working on the same project and maybe you need to share the same image file. Instead of keeping 2 copies, one copy in your directory and another copy in your partner's directory, maybe what you can do is let him or her keep the file and then you link his file or her file to your directory. And the benefit of using this approach is whenever your partner replaces the image with a new one, then your link will always refer to the same latest copy. And I just want to emphasize here that making a link to a file is not copying the data of that file. You can create 2 kinds of links in Unix, hard links or symbolic links. I'll be using this example again. Let's say currently in your project's subdirectory, you have these files in black and you want to create links to the current file shown in red here. To create a soft link, you will use the ln command and you will say ln -s. -s is for soft link or symbolic link. And the next argument is the original file, or we call it the source file. And then the next argument is the name of the link. And to create a hard link, you will be using the same command, but without the -s option. So again, this will be the source file, and this is the name of the link. So term.c will be a hard link to the original C program. So what is the difference between the two? Let's say the directory entries of the project's subdirectory is shown in green. When you create a symbolic link, the system will create a new inode, and just remember that a new inode means a new file. The inode 8881 is now associated with a new file, and the content of that file is just the path to the source file. So what happened in your subdirectory's project, a new entry, unode.c, will be created with this new inode number, and that inode will point to this inode structure, and the permission mode of a symbolic link will be displayed as an L with an L at the beginning, and the rest of the metadata will be filled with the appropriate data. So if you create this link at 2016 February 17, and that will be the date that you will see here, the size in the metadata is the size of the file. With a symbolic link, the file content is just the path to the source file. And if you count the number of characters in the file name CS452 all the way until the last C, you will see a total of 16 characters in here. That will be the content of the new file, which is unode.c. So that's why the length of the file will be 16. How about the hard link? When a hard link is created, the system will not create a new inode, but what happened is the current inode of the source file will be identified, and in our example, the inode of program1.c is inode 4512. So then when a hard link is created for term.c, the file system will create only a new directory entry without creating a new file. And in that directory entry, the name of the file will be term.c, but the inode number will be the inode of the source file. So here, that's why you see the number 4512 in both directory entry for term.c and then program1.c. And as a side effect of adding a link, the link count will go up from 1 to 2. So originally this number is 1 before you create the hard link term.c, but after the hard link term.c is created, the file system will update the link count from 1 to 2. So how do you choose between hard links and soft link? So hard links will work only within the same file system. It's not going to work across two different file systems. So let's use this as an example. So let's say you have two hard drives attached to your machine, and the first drive is where you have your home directory, and the second drive, disk number 2, is where all the applications are installed. What happens if you want to create a link to your favorite file, favorite game Sudoku, and let's say the Sudoku game is installed in the second hard drive at this location, apps game Sudoku, and the inode number for that file is inode 3950. Remember, hard link will just make a new entry in the first drive by copying the inode from the source file. That means what happened here, hard link will create a new entry under the name of, let's say, home me bin Sudoku, and it will be associated with the inode number 3950, but inode 3950 is not the inode of the Sudoku game. Let's say if inode 3950 is the inode for the Firefox browser, then that link will effectively create a link to your Firefox, not to the Sudoku game in the other file system. So for this case, you have to use a soft link. If you create a soft link, then the system will create a new file in the first file system, and the content of that file will be the path to the Sudoku game in disk number 2. How do you prepare a disk or a partition in a disk to be formatted for a specific file system? Remember, formatting for a file system is just organizing your disk block, certain disk blocks for a certain purpose. In a Unix file system, these 4 blocks must be prepared. So the first block is the boot block. The boot block will allow you to boot your Linux operating system to run. And the super block is a special block where it keeps the information about the free block, the free inode block, the free data blocks, and also the location of the root directory. And then the inode blocks, as we mentioned before, inodes and data blocks are different. That's why some of the disk blocks must be prepared to be used for inodes, and some of the disk blocks must be prepared to be used for data blocks. And among these different blocks, the majority of these blocks will be used for your data. Let's look at a different problem, how a path name is resolved at runtime. Again, we're going to be using the structure from the Unix file system. So let's say you have a file whose absolute path is /home/hans/hello.c, and you want to fetch this file or open this file in your editor. So we have to start from the root directory, but how do we find the inode from the root directory? It is in the super block. In a traditional Unix file system, the inode of the root directory is inode 128, but on a Linux machine, the inode of the root directory is inode 2. So we start from the super block to go to the root inode, and once we have the root inode, we're going to use the pointer, data pointer, to look at the data in the root directory. And let's say currently in our root directory, we have these files, home, lib, usr. We are searching for home, and the directory entry for home will take us to inode 943. We have to open inode 943. We are going to be using the data pointers, and that will take us to the directory entry of home. And again, under home, we will search for Hans, and that will take you to inode 466. And inode 466, you'll be using the pointers to the data block that will take you to the directory of Hans. And under that directory, you will search for a directory entry hello.c that will take you to inode 2921. And inode 2921 is associated with the C file, and using the pointers to the data block of the C file, then you will be looking at the actual source code of the C file. The ability of the Unix file system to handle extremely large files is made possible by indirect blocks and indirect pointers. An indirect block is a data block that is used for storing pointers to more data blocks. An indirect pointer is a pointer that points to an indirect block. The difference between single, double, and triple indirect pointers is the depth of the indirection. This diagram should remind you of your data structure course on trees. And this page is an illustration of a ternary tree when a node can point to 3 children. When the height of the tree is only 1 level, the number of nodes is only 3. But if you go deeper to 2 levels, then the number of nodes at this level is now 9. And if you continue to make the tree deeper to 3 levels, and the number of nodes at this level is now 27, which is 3 cubed. And if you keep going, make the tree deeper, and the number of nodes at this layer, the purple nodes, will be 81, or 3 to the power of 4. My apology to use this illustration of the coronavirus. If one person can infect 3 other people, and each person at that layer can infect 3 other people, then you can see that the number of infected people will grow exponentially. Let's look at how the data pointers are used inside the inode. So for this illustration, we will assume that the data block size is 2 kilobytes, and we are using a 4-byte pointer, and therefore each data block can be used to hold 512 pointers. How do I get 512? just 2 kilobytes, which is 2048 divided by 4, and you will get 512 pointers. And we have 12 direct pointers. Each of these pointers will point to a data block of size 2K. From the 12 direct pointers, you will get at most 12 blocks of data. If you use the single indirect pointer, that pointer will point to an indirect block, and that indirect block can hold up to 512 pointers. And each of that pointer will point to one data block. So from the single indirect pointer altogether, you can get up to 512 blocks. If you use the double indirect pointer, that pointer will point to one indirect block, but each of the pointer inside that indirect block will point to another indirect block. So altogether, we have 512 indirect blocks from here. But remember, each of the indirect block here can hold 512 pointers. That means altogether, if you combine all the pointers in the second layer index block, then you will be able to get as many as 512 square blocks. Now, using the same analogy, if you use the triple indirect pointer, that pointer will point to one indirect block holding 512 pointers, and each of that pointer will point to one indirect block. So at this level, you will be able to get 512 indirect blocks. And if you keep going to the next level, and eventually you will be able to get as many as 512 cube blocks. Let's summarize the layout here. So from the direct pointers, you will be able to get 12 data blocks. From the single indirect pointer, you will be able to get 512 blocks. And from the double indirect pointer, you will be able to get 512 square blocks. And from the triple indirect block, you will be able to get 512 to the power of 3 number of blocks. And 512 depends on the size of your block. Now let's take a look at two different scenarios. So let's say in the first scenario, the size of the data block is 2K, which is 2048. And we're going to assume that each pointer is a 4-byte pointer. That means each block can hold up to 512 pointers. You just divide 2048 by 4, and the 12 direct pointers will be able to give you 12 blocks of 2K each. So the capacity of that data blocks will be 24K. Using the single and direct pointers, you will be able to get 512 blocks of size 2K each, and 512 is 2 to the power of 9, and 2K is 2 to the power of 10. If you multiply the two numbers, you get 2 to the power of 20, and 2 to the power of 20 is 1 meg. From the double indirect pointers, you will be able to get 512 square number of blocks. And if you multiply that by the size of each block size, 2K, you will get 2 to the power of 18 from that number, and 2 to the power of 11 from that number. Then the product is 2 to the power of 29, and that is equivalent to 512 meg. And from the triple indirect pointers, you'll be able to get as many as 512 cube number of blocks. If you multiply by the block size, you will get 2 to the power of 27 from the first number, 2 to the power of 11 from here, and the product is 2 to the power of 38, and that is equivalent to 128 gig. So the total capacity will be 128 gig plus 512 meg plus 1 meg plus 24K. So this is the total size that you can create in a Unix file system when the block size is 2K and the pointer is a 4-byte pointer. Now let's look at the second example. Assuming we have a bigger data block of size 4K and we are using the same pointer, 4-byte pointers, that means each block can hold up to 1024 pointers. And from the 12 direct pointers, you will be able to allocate as much as 12 times 2 to the power of 12, and this will give you 48K. From the single indirect pointer, you will be able to allocate 1024 blocks, and the capacity of each data block is 4K. If you multiply the two number, then you will get 4 meg. And from the double indirect pointer, you can get as many as 1024 to the power of 2 multiplied by the capacity of each data block, and if you do the math, the total is 2 to the power of 32, which is equivalent to 4 gig. And from the triple indirect pointers, you will be able to get as many as 1024 cube number of blocks multiplied by the block capacity. This is the total, 2 to the power of 42, which is equivalent to 4 petabyte. So the maximum file size on this system would be 4 petabyte plus 4 gig plus 4 meg plus 48K.